So today's video is going to be over the kinetic molecular theory of matter. So again, we're going to be discussing matter, and we're going to be discussing the states of matter in a little bit more detail than we've already covered it. So let's just go back through here. Matter is made up of particles which are in constant random motion. So they're all moving in some form or another. It can be defined as anything that has mass or occupies space. Matter is classified by its state and its type, of which there's three main ones we're going to talk about: solid, liquid, and gas. And of course, there is a fourth one, plasma, but we typically don't talk much about that in here. So the three states, again, are solid, liquid, and gas. So let's talk a little bit about solids. Their substances have their own shape. Sulfur, copper, wire, ice, all of those, they have their own shape. Liquids take the shape of their container. So if you have water, it doesn't matter what kind of a container you have, it's going to take its shape: alcohol, bromine, and mercury. And then you have your gas, which are spread out to occupy any available space that they have within that container. So our gases are like oxygen, carbon dioxide, and helium. Now let's get a little bit more into detail. So when we talk about solids, particles in a solid are closely packed in a regular arrangement known as a lattice. So here you can see a water molecule and how the particles are all fixed together. And if you think of, we talked about like strength and so forth, how strong that would be. Also thinking about the movement of it when it's that way, how easily it can move compared to these. So this one cannot move very easily, whereas you see these are going to be moving a lot more. And when you talk about the structure, how this is very fixed, where these over here are not. So that's what we're going to be comparing those. So again, the particles in a liquid are not closely packed, and they are irregular in their arrangements. Where gases, the particles are very separated. So here's what we're going to talk about as far as the kinetic molecular theory. So kinetic energy means energy of motion. So when we're looking at a solid in its, again, rigid shape here, we're going to have to add energy to change it to a liquid. Now, that energy is going to be heat energy, whether it's coming from the surroundings or whether we're putting it on a hot plate. Then you have your liquid, which are not near as fixed. They're able to take the shape of the container. And when we add, again, more energy to that, they become gases. And again, a gas then will fill the entire container. Now, a liquid won't fill the container. It's only going to have whatever volume it happens to have. But a gas, the particles will spread out so much that it actually does fill the container. And then again, if you add more energy, now we start talking about plasma. Which when we start talking about plasma, we start talking about the gain and loss of electrons and so forth. And again, here is your energy. So the more energy we put in, we're changing it through its phases. Again, that's why it's called the kinetic molecular theory of matter. Okay? We're putting kinetic energy, or we're putting heat energy in it to make these have more kinetic energy, more energy of motion. So when we talk about the forces, so in a solid, the forces are strong enough to keep the particles in a fixed position. I showed you that picture earlier. Particles do, however, vibrate and rotate in their position. So a lot of people think that when we're talking about a solid, if you think about your textbook or the table or your desk or whatever, you think, well, those particles, you can't see them moving. But in fact, they're vibrating. I use a good example of this, I think, if you were at a concert maybe in which there was tons of people and you're just cram-packed in. You know, even though you're packed in, you can still move slightly. You're not going to be able to go very far, but you can. So we call that like vibrating in terms of our atoms. Okay, you can move, but not very far. Then in your liquid state, there's a weak force which holds them together. And so the greater the energy of the particles and the weaker the force allows that disruption of the lattice and the particles. Therefore, the particles start sliding past one another. So again, that might be where there's not quite as many people at the concert. And so you can kind of move in and out of it and go from one place to the other. It's going to take some effort to move through, because you're still bumping into other particles or other people, but you can move, okay? Then our final one again is the gaseous state, and these particles possess even higher energy levels, and the forces which hold the gases are pretty much negligible. In other words, really those forces, they're there, yes, but we're really not going to notice them. And so that might be where you're just out running around going wherever you want to go, maybe think of little kids when they just get sent out on recess and they just start going all over the place. Filling up the entire playground. So this explains why gases are able to isolate themselves completely from one another and have no fixed shape or size. Now again, when we call those change of state, you also hear them called as phase changes. They do involve the heat energy that you do have to supply, or you could remove it. So if you're going from a gas to a liquid to a solid, you would be removing the energy. Increasing the amount of heat energy in a substance increases its kinetic energy. Again, the more energy, the more heat you give it, the more energy you're going to give it, since the temperature is defined as the amount of the measure of kinetic energy that a substance has. So again, think of you, if you're out running around, having more energy, you're moving faster and faster, you're going to get hotter and hotter. Okay, so kinetic energy, heat energy, as one increases, the other is going to increase. We've got a little picture here to show the different change of state. So this is melting, okay? And you're going to see this a lot. So you're going to need to be able to complete a chart, if not this one, then something similar to this chart. So in a solid, heat energy causes the particles to vibrate at a greater rate until they possess significant energy to break away from their fixed position and become a liquid. This is known as melting. This here we are, we're at a solid, and when we're adding energy, okay, we're becoming a liquid. Now, enthalpy of a system means the amount of disorder. So you can see that this is going up. So when we're in a solid, we're very rigid, we're in a fix. That's kind of like maybe we're sitting here in our rows, in our desk in a rows in a fixed pattern. Where the liquids, maybe these are when we've got them in our pods of 3. We're just a little bit more disordered, okay? So the temperature at which this occurs is called the melting point. We've already talked about that. Melting point for water is 0 degrees. Okay, now freezing, okay, is just the opposite of melting. So heat this time is removed from the liquid and the particles are returned to their closely packed fixed position. This is called freezing, going from a liquid to a solid. Again, in terms of your enthalpy or your disorder, you're decreasing your disorder. You're becoming more ordered here. Okay, then we have vaporization, is when heat energy is supplied to a liquid. The particles also take on more heat energy, which causes them to move around more quickly. So again, vaporization, you're going from a liquid to a gas. Fast-moving particles at the surface of the liquid eventually have significant energy to escape the liquid and move into their gaseous phase. Now, one of the things that one of the class talks about, maybe not all of them, is somebody said, well, isn't that boiling? Boiling is actually within the liquid. And if we need to, we can talk more about that. So boiling is within the liquid, where vaporization is once the particles leave the surface, okay? So they're going to escape the surface of the liquid, and then they're going to become liquid, or they're going to become a gas. That's called vaporization. That's spelled wrong there. Okay, so going from a liquid to a gas. Okay, then we have condensation, of course, which is just the opposite. That's when we go from the gas to the liquid. Heat is removed, particles go back closer together. We talked about an example of condensation. Could be like if you've got a cold pop that you're drinking a soda on that, in which you have that condensation that occurs on the edge of your container. That occurs because the gas surrounding your pop is warmer than your pop is. So when the gas hits your pop, it cools it down. And so it's taking it from a gas to a liquid. And that's what you see on the outside of your container. So it's the gas in the air, okay, your air that is gas, I should say, becoming liquid. You see the same thing on your cars in the morning, okay, condensation. So that is when the air outside is warmer than your vehicle or the glass, So when it hits your glass, again, it cools down to its liquid phase. Now, again, you're going to have to be able to give examples of some of those. So I just gave you 2 good examples if you jot those down. Okay, then we have sublimation, and a lot of you guys have probably heard of sublimation. Substance such as iodine crystals are able to change from a solid directly to a gas, without moving through the liquid phase. And most of you guys think of that as we're going from solid to straight to the gas. Most of you guys think of dry ice, maybe when you see that. So your dry ice, which is solid carbon dioxide, will skip the liquid phase and it will go straight to a gas. And then we have just the opposite, which is deposition, which goes just the opposite. It is a reverse. It's when it goes straight from a gas to a solid. And again, it says an example of this can be seen in sub-zero temperatures when water vapor in the air changed directly to ice without becoming a liquid. That could be some of you guys, if you've ever been out in the really, really cold, and which maybe it's raining or something. I think of men with beards. It seems like that it goes straight to the air. It gets so cold that it goes straight to the solid on their beards. That happens. Okay, so that's adding in those 3. And again, you're going to need to be able to describe all 6 of them in the order in which they go. Again, remembering that, again, enthalpy means the disorder of the system. So a solid is definitely more ordered, a liquid is more disordered, and then a gas, of course, has the most in terms of disorder of the 3 of them. The last one that we don't, again, talk much about is plasma. We're going to go ahead and hit it real quick. Plasma-like gas has no fixed shape or volume. A gas can reach the plasma state when its atoms become ionized. Now, right now, you might not know what ionized means, but that is when they lose electrons and become positively charged. So we'll talk about ionization as we start talking about the periodic table and protons, neutrons, and electrons. Recombination occurs when plasma returns to its gaseous state. So again, those are the 2 up here. Okay. Examples of plasma, again, are your neon lights that you see. The electricity flows through the gas tube containing the gas, stripping the atoms of their electrons. So that might be your neon, your argon, krypton, xenon, so forth over there on your noble gases. Electricity promotes the electron to a higher energy level. As electrons return to its former energy level, the excess energy is carried away into photons, which we see as colored light. And again, we'll do an activity where I will show you an example of where we see those photons and that colored light being given off. So we'll do an activity where you can actually see that, and we can see what color each of the different elements, well, not all of them, but some of the elements give off.